So we're now ready to talk about how parallel programs are developed in Java. And this will be done in 3 parts because there are 3 key frameworks we're going to be talking about in this course, so I broke them up one by one. The first topic we're going to cover is really not covered very much directly in this course. We will cover it a bit, but it's covered in my sister course. You'll see why. And that's the topic of fork-join pools, or fork-join thread pools. And fork-join pools are an object-oriented data parallelism framework. And that's why we don't cover it very much in this class, because this is a functional programming, parallel programming course. But I'll give you a quick overview of this, because it does actually occur underneath a lot of the other stuff we're going to cover. So the fork-join framework defines an object-oriented parallelism model. What the heck does that mean? Well, we'll talk about what that means in a second. If you want to learn lots more about the fork-join pool that I will have time to cover in this course, please take a look at this link by my good friend Doug Lee, who developed most of the concurrency and parallelism stuff in Java. The fork-join framework provides a high-performance, fine-grained task execution model. If you recall before, when we talked about earlier versions of Java, I talked about how they had coarse-grained execution, where the expectation was there were a relatively small number of cores, 2 to 4. With this model, we can scale up to many more cores compared to the older way of doing things. And that's the reason why this is so important. The focus in the fork-join framework is something called data parallelism, where data is partitioned across multiple threads and cores, which then operate on the data in parallel. Back in the old days, at the hardware level, we used to talk about single instruction, multiple data style hardware architectures. And you can think of data parallelism as a software variant of that pattern. Single instruction, multiple data. The key abstraction in the fork-join framework is the fork-join task, which is a class. And a fork-join task is a lighter weight unit of execution than a Java thread. So if a Java thread was pumped up on steroids and human growth hormone, the fork-join task would be like the much smaller sibling who's a little bit scrawnier, maybe a little scrappier in some ways. But the key point is that the thread has a runtime stack, it has its own registers, it has its own thread local storage, whereas a fork-join task does not. So it's much lighter weight. Therefore, a very, very large number of fork-join tasks can run in a much smaller number of actual Java threads, worker threads, in a fork-join pool. So that's why we have the fork-join task model. So you could have hundreds of thousands or millions of these things. You couldn't really have hundreds of thousands of millions of threads in most environments, but you could have hundreds of thousands of fork-join tasks. And this just a quick side note. Remember we talked before about Java virtual threads versus Java platform threads. Java virtual threads, at least at the moment, are implemented using fork-join tasks. That's just a side note. I don't really expect you to know that, but it's a good thing to keep in the back of your head. The fork-join framework supports parallel programming using a divide and conquer model to parallel processing. And you're probably familiar with divide and conquer model if you've taken the data structure course here, you've taken the algorithms course here, or you've taken those courses elsewhere. You talk about divide and conquer algorithms. A good example would be things like quicksort or merge sort, where you take a big problem, you split it up into smaller problems, and you solve them all potentially concurrently. You don't have to, but you could. So this is how the fork-join model works. You have a big problem to solve. If the problem is small enough, just solve it. So at some point, you split things up into small enough chunks. You can solve each chunk sequentially. Otherwise, take the overall problem and split it up into multiple parts, chopping it up into little pieces, hopefully efficiently and evenly. And then fork new subtasks to solve each part, and of course, allocate those subtasks to run on the cores in the underlying hardware, so they run in parallel. Then you join all the subtasks together, so you get all the results from the subtasks, and you start assembling them together. And then you finally get a single reduced result from all the sub-results that you joined. And if you play your cards right and you split things evenly, and you've got a nice infrastructure for doing all this stuff, and you've got a problem to solve that is recursively splittable in this way, with something called embarrassingly parallel capabilities, then you can end up with computing the result very quickly, and maybe even in a time that's going to scale by the number of cores you have at your disposal, which is really great. Okay, so that was a quick overview of the fork join framework. Let's talk about the pros and cons briefly. So what are the pros of the fork join framework? Well, the pro is that it employs something called work stealing to maximize multi-core processor utilization. And what work stealing does in a nutshell is to be able to have a bunch of threads. These are Java threads, worker threads, not fork join tasks. And they each have a double-ended queue called a deck. And I won't go into the details at the moment of how the deck works, but it's very cool. And if a thread runs out of work to do in its deck, rather than just sit there idly and spinning or sleeping, it'll look around to the other decks owned by the other threads in the pool and try to steal their work. And if it goes well, it'll steal the work from the end of the other thread's deck. And that way it won't affect what the thread is doing on the front of its deck. It'll steal from the end. And that way you can get more work done because things are always busy. The common fork join pool, there's something called a common fork join pool, which we'll talk a lot about when we talk about parallel streams and completable futures and so on. That can also be grown and shrunk automatically using something called a managed blocker. So that gives you some flexibility that lets the system auto-scale itself. And we talked about auto-scaling and being able to scale up under different workloads. Of course, not everything is unicorns and rainbows, so there are some cons. One of the problems is it's potentially tedious and error-prone to program the fork join framework. And the reason for that is this was added to Java in Java 7, which was 2010-ish timeframe, and that was about 4 years before Java functional programming became a thing. And as a result, you have to use object-oriented programming techniques based on inheritance and subclassing, which is a white box approach to this. So there's this thing called a fork join task, and then you have to have subclasses of that, which you have to fill in, and et cetera, et cetera. And therefore, it's not integrated with Java's modern functional programming features. So it's a little bit tedious to program. You will not have to worry about that in this class because all that stuff is hidden from you, thankfully. So overcoming the cons of the fork join framework, the programming cons, the performance cons, there really aren't a lot of performance cons. Performance is great. It's the programming that's tedious. And the reason it was tedious is because they couldn't take advantage of the functional programming features, because they weren't in Java at that point. But later, in Java 8, which came out in 2014, they added other functional programming features. And so you can basically think about these other features like parallel streams and completable futures as encapsulating the object-oriented fork join pool with a functional wrapper, making it a lot easier to program. So that's the end of the discussion of how parallel programs are developed in Java. Part 1. So we have a couple more parts that we'll go through today.